welcome. In this session, we'll explore how to apply our simple two-layer neural network to some data. Here, imagine that we have not just one data one form, but we have multiples, and we'll subscript them with the letter I. So for each one form x sub I, it has a label y sub I that is either 0 or 1. The descent vector that we can compute through the whole neural network, we'll say, is d sub I. And what we do is we sum all of these descent vectors for all of these data and get a single descent vector, d. We then take one step with fixed step size. This is the standard to do in neural networks. And what that means is that our new estimate of the overall neural weight vector is the previous one plus the learning size or step size times this overall descent vector. Let's take a look at some classic data. So in neural networks, this goes all the way back to Rumelhart with the perceptron, where it was observed that there's a simple kind of data that is not linearly separable and that a single neuron can't have. So let's suppose that we use two layers, and what we'll do is we'll use two hidden neurons in that hidden layer. So here's an example of the data. Here we have the labels +1, which are in these quadrants, and here we have the label 0 in the other quadrants. Visually, you can see that a single neuron isn't going to be able to separate these with a single hyperplane. So what we do is we run our neural network on this data, and we do it again and again. And what we end up with is we find that this is what's happening, is that the layer 2, the hidden layer, are performing two different linear separability criteria. One is it's separating these pluses from everything else. The other neuron is separating these pluses from everything else. Please observe that I didn't instruct the network on how to do that. The network figured it out all by itself. And it was done by using this method of steepest descent that we've applied in this course. So we can also visualize this in a different way. We could use the colors cyan and magenta to say what is happening to the weights in that hidden layer, and then we could use white to say what's happening in the output layer. What we find is that as with many descent problems, it'll rapidly approach a minimizer and then it'll slowly converge. And this is what happens, is that the weight vector will start here, so it's in 3D because we have 2D data and then we're appending a 1 onto it, right? So when we do that augmented data, we get 3D. So this is the trajectory of hidden neuron 2, this is the trajectory of hidden neuron 1, and this is the trajectory of the output neuron. So we can see that in the case of the output neuron, it makes one mistake and then slowly converges to the result, and then the hidden layer is slowly converging to its result, and we're able to use a simple neural network to solve a classic non-separable problem. How can we summarize everything that we've learned in this lecture? Well, one is that the hidden layer is really a linear array of transfer functions. That's really what's going on. And when we're going through the Jacobian and using the Hadamard product, all of it comes down to using linear algebra to solve this problem, which is a layer of neurons is a vector. The output of a layer is an observation to the next layer. So for our hidden layer, it goes to the output, but any response of a layer is an input to a previous layer, and that's how deep neural networks work. Each layer will augment the descent direction independently of the other layers. So there's a certain dependence in the sense of some weights and back terms going back and forth, but these are each one of these is adding to the whole solution. And a caution that we'll go through in subsequent lectures is that the derivatives can be very nearly 0 if we use the sigmoid activation function, which is the classic activation function for artificial neural networks.